This is Sleepy Space, a slow space story to help you fall asleep. Look up on a clear night, far from city lights, and you might notice a faint smudge of light in the constellation Andromeda. It appears as little more than a blur, a soft glow barely distinguishable from the surrounding darkness. Most people pass over it without a second thought. That small patch of light is not a star. It is not a cloud. It is another galaxy. An entire collection of stars, hundreds of billions of them, suspended in space more than 2 million light-years away. And it is not standing still. At this very moment, the Andromeda galaxy is moving toward us. The light reaching your eyes tonight began its journey more than 2 million years ago. When it left those distant stars, early humans had not yet learned to farm. Stone tools were still new. Entire civilizations would rise and vanish before that light ever arrived here. And now, after crossing the emptiness of intergalactic space, it reaches Earth carrying a quiet but unsettling message. Andromeda is coming. It is our nearest major galactic neighbor, a vast spiral galaxy similar in size and structure to our own Milky Way. Like our galaxy, it contains a dense core, sweeping spiral arms, and a supermassive black hole at its center. It stretches across more than 200,000 light-years of space and contains roughly 1 trillion stars. From Earth, it appears small only because of distance. If the human eye were sensitive enough to see its full extent, Andromeda would span an area of the sky several times wider than the full moon. Most of it is invisible to us, fading quietly into darkness. But distance does not mean separation forever. Astronomers have known for less than a century that Andromeda is not drifting randomly through space. By examining the light it emits, they can detect its motion. When an object moves toward us, its light shifts slightly toward the blue end of the spectrum. This effect, known as blue shift, is unmistakable in Andromeda's light. The measurement is clear. The galaxy is approaching the Milky Way at roughly 250,000 miles per hour. By human standards, that speed is extraordinary. A passenger jet crosses continents at a fraction of it. But space is vast beyond intuition. And even at that velocity, Andromeda remains unimaginably far away. The collision will not happen tomorrow. It will not happen in 1,000 years. It will happen in approximately 4 billion years. 4 billion years is a number so large it almost loses meaning. Complex life on Earth has existed for only about 500 million years. Dinosaurs appeared, dominated the planet, and vanished entirely within a fraction of that time. Human civilization, with all its cities, languages, and technologies, occupies barely 10,000 years. A fleeting moment on cosmic scales. And yet, the approach of Andromeda has already been underway for far longer than human history. Long before the sun ignited, long before Earth formed from dust and rock, long before the first oceans condensed beneath an alien sky. The gravitational pull between these two immense galaxies has been drawing them together across billions of years of cosmic time. Gravity does not rush. It does not need to. It works patiently, constantly. And when two massive structures exist relatively close together by cosmic standards, the outcome is inevitable. Over time, even the faintest gravitational attraction becomes decisive. The Milky Way and Andromeda have likely been destined to meet since the earliest stages of their formation. For most of human history, we did not even know Andromeda was a separate galaxy. It was once thought to be a nebula, a faint cloud of gas drifting somewhere within our own Milky Way. Only in the early 20th century did astronomers realize the truth. That faint smudge of light was another island of stars entirely, far beyond the boundaries of our galaxy. That realization changed our understanding of the universe forever. The cosmos suddenly expanded. The Milky Way was no longer the whole of existence, but just one galaxy among countless others. And as measurement techniques improved, we learned something even more unsettling. Not only was Andromeda separate, it was approaching. This collision is not speculation. It is not a distant theory that may or may not prove true. It is written into the mathematics of gravity and motion. Given enough time, the two galaxies will meet. But what does it actually mean when galaxies collide? Despite the word, such an event is not like planets crashing together or stars smashing head-on. Space within galaxies is mostly empty. Individual stars are separated by enormous distances. When two galaxies merge, stars usually pass by one another without direct impact. But gravity reshapes everything. As the Milky Way and Andromeda begin to interact, their spiral structures will distort. Long streams of stars will be pulled outward into space. New waves of star formation will ignite as clouds of gas compress and collapse. Over hundreds of millions of years, the two galaxies will lose their distinct identities. The Milky Way, as we know it, will cease to exist. In its place will form a single, larger galaxy, a new structure born from the slow destruction of two ancient systems. Our night sky will change beyond recognition. Constellations will stretch and dissolve. The familiar band of the Milky Way will fade into something entirely different. By the time this process is complete, Earth itself may no longer exist. The sun will be nearing the end of its life, swelling into a red giant. If humanity survives at all, it will not be here to witness the final merger. And yet, the story of that collision is already written. To understand what is coming and what it means for our place in the universe, we first need to understand what we have now. The structure of our own galaxy. The delicate balance that allows stars, planets, and life to exist within it. Before the Milky Way is torn apart and reborn, we must understand the home we are destined to lose. The Milky Way is home. It's the only galaxy most of us will ever truly know. From our position inside it, we see it as a band of light stretching across the night sky, a river of stars too numerous to count. Ancient cultures saw it and named it. The Greeks called it galaxies, meaning milky circle. The Romans named it Via Lactea, the road of milk. We've been looking up at our own galaxy for as long as we've existed, but seeing it from the inside makes it difficult to understand what it really is. We're embedded within it, looking out through layers of stars and dust and gas. For a long time, we didn't even know the Milky Way was a galaxy, didn't understand that those stars formed a distinct structure. We thought we were simply surrounded by stars in all directions, with no particular shape or boundary. We know better now. The Milky Way is a barred spiral galaxy, meaning it has a central bar-shaped structure with spiral arms extending outward from the ends of that bar. The whole thing measures roughly 100,000 light-years from edge to edge. That's the distance light travels in 100,000 years. moving at 6 trillion miles per year. The numbers become too large for intuition. We can state them, but we can't really feel them. Our galaxy contains somewhere between 200 billion and 400 billion stars. The uncertainty exists because many stars are hidden behind clouds of dust, or too dim to detect easily, or clustered so tightly they blur together. But the general scale is clear. Hundreds of billions of individual suns, each potentially with its own system of planets. Our sun sits in one of the outer spiral arms, about 26,000 light-years from the galactic center. We're not in some special location. We're out in the suburbs, so to speak, far from the dense core where stars pack together much more tightly. This is actually fortunate. The galactic center is a chaotic place with radiation and gravitational forces that would make stable planetary systems difficult. Out here, in the quieter regions, life has room to develop. The galaxy rotates, all of it. Stars orbit around the galactic center just as planets orbit around stars. Our sun, along with its family of planets, completes one full orbit, roughly every 225 million years. We call that span a galactic year. In the time since dinosaurs first appeared on Earth, our solar system has completed only about one galactic orbit. In all of human history, we've moved through barely a tiny fraction of that vast circle. The Milky Way isn't just stars, though. Most of what makes up our galaxy is actually invisible. Vast clouds of gas and dust fill the spaces between stars, especially in the spiral arms. These clouds are the nurseries where new stars form. Gravity causes the gas to collapse inward, becoming denser and hotter until nuclear fusion ignites at the center. A star is born. This process continues constantly throughout the galaxy, creating new generations of stars even as old ones die. At the very heart of the Milky Way lies something we can't see directly: a supermassive black hole called Sagittarius A star. It contains the mass of roughly 4 million suns compressed into a region smaller than our solar system. Despite its enormous mass, it's quiet compared to black holes in some other galaxies. It occasionally consumes gas or tears apart a wandering star, releasing bursts of radiation, but mostly it sits dormant at the center of everything, holding the galaxy together through its gravity. The galaxy also has what astronomers call a halo, a roughly spherical region surrounding the disk where the spiral arms reside. This halo contains old stars, arranged in clusters that orbit the galaxy in elongated paths. It also contains most of the galaxy's dark matter, a mysterious substance we can't see but know exists because of its gravitational effects. Dark matter may actually outweigh all the visible matter in the galaxy by a factor of 6 or more. We don't know what it is. We only know it's there. The Milky Way doesn't exist in isolation. It's part of what's called the local group, a collection of more than 50 galaxies bound together by gravity. Most of these are small dwarf galaxies containing only millions or billions of stars rather than hundreds of billions. They orbit around the two dominant members of the local group. One of those dominant members is the Milky Way. The other is Andromeda. These two large galaxies are by far the most massive objects in our corner of space. Together, they account for most of the local group's total mass. The smaller galaxies are satellites, held in orbit by the gravity of the larger ones. Some of these satellites are slowly being torn apart, their stars gradually absorbed into the larger galaxies. It's a process that's been ongoing for billions of years. Our galaxy is dynamic. It's not a static structure frozen in time. It rotates, it forms new stars, it absorbs smaller galaxies. The spiral arms shift and change over millions of years. Gas flows inward toward the center, gets heated and pushed back out by radiation from newborn stars, then cools and falls inward again. Everything is in motion, everything is evolving. And like Andromeda, the Milky Way is traveling through space. We're not just rotating, we're moving as a unit, pulled by the gravitational influence of nearby galaxy groups and clusters. The exact path is complex, affected by multiple gravitational sources, but the general direction is clear enough. We're falling toward Andromeda, just as Andromeda falls toward us. Both galaxies have been on this path for a very long time. Neither formed in isolation. Both have grown over billions of years, shaped by their own histories of collisions and mergers with smaller galaxies. To understand what's coming, we need to understand where both galaxies came from. The Andromeda galaxy is larger than ours, significantly larger. It stretches across roughly 220,000 light-years, making it more than twice the diameter of the Milky Way. It contains approximately 1 trillion stars, perhaps more. Where our galaxy holds hundreds of billions of suns, Andromeda holds close to 1 trillion. It's the dominant member of the local group, the largest and most massive galaxy in our cosmic neighborhood. From Earth, Andromeda looks small only because of distance. 2.5 million light-years separate us from it. That's the distance light travels in 2.5 million years, crossing a void so vast that almost nothing exists within it. A few stray stars, perhaps, expelled from their home galaxies. Some hydrogen gas, spread thin across the emptiness. But mostly, the space between the Milky Way and Andromeda is just that, space. Dark and empty and cold. Despite the distance, Andromeda and the Milky Way have always been connected. Gravity reaches across the void. It doesn't weaken with distance as quickly as other forces. Two massive objects separated by millions of light-years still pull on each other, still influence each other's motion. That pull has existed since both galaxies formed, and over billions of years, it's been drawing them together. Andromeda is a spiral galaxy, like ours, but its structure is slightly different. Its spiral arms are more tightly wound, more clearly defined. It has a larger central bulge, a denser core where stars pack together more closely. At the very center, like our galaxy, it harbors a supermassive black hole. But Andromeda's black hole is much larger than ours. It contains the mass of tens of millions of suns, possibly even more than 100 million. The exact number is difficult to measure, but the scale is clear. Andromeda's central black hole dwarfs our own. Both galaxies have grown over time. Neither began as the large spiral structures we see today. In the early universe, galaxies were smaller, more chaotic, less organized. They grew by consuming other galaxies. Mergers have been happening since the first galaxies formed, and they continue today. It's one of the primary ways large galaxies develop. We can see evidence of past collisions in the structure of both galaxies. The Milky Way has streams of stars in its halo, remnants of smaller galaxies it absorbed long ago. These streams trace the orbits of galaxies that were torn apart by tidal forces, their stars scattered but still following the paths they once traveled. Some of these streams are billions of years old, fossils of ancient collisions that shaped our galaxy's current form. Andromeda shows similar scars. Its outer regions contain structures that don't match the smooth spiral pattern. There are loops and shells of stars, concentrations that shouldn't exist if the galaxy had grown slowly and peacefully. These are the remains of smaller galaxies Andromeda consumed. Some of these mergers happened billions of years ago. Others are still ongoing. The Magellanic Clouds visible from Earth's southern hemisphere are small galaxies currently orbiting the Milky Way. They're not permanent fixtures. Eventually, over hundreds of millions of years, they'll spiral inward and merge with our galaxy. Their stars will become our stars. It's a slow process, but it's inevitable. Gravity always wins given enough time. Andromeda has its own satellite galaxies and it's consuming them as well. One called Messier 32 is particularly close to Andromeda's core. It's being stretched and distorted by tidal forces, slowly pulled apart. In time, it will disappear entirely, its stars absorbed into the larger galaxy. This is happening right now, visible in our telescopes, a merger caught in progress. These smaller collisions are common. Large galaxies like ours and Andromeda have been growing through such mergers throughout their existence. But what's coming is different. When the Milky Way and Andromeda collide, it won't be a large galaxy consuming a small one. It will be two giants of roughly comparable size meeting head-on. Neither will simply absorb the other. Both will be transformed. The space between our galaxies seems empty, but it's not completely void. There's gas. Thin, spread out, barely detectable, but present. Hydrogen primarily, the most common element in the universe. Some of this gas may have been stripped from the galaxies themselves by gravitational interactions. Some may be primordial, left over from the early universe. Either way, it fills the gap, a tenuous bridge between two massive structures. Both galaxies are embedded in larger halos of dark matter. We can't see this dark matter, but we can detect its gravitational influence. It extends far beyond the visible edges of each galaxy, forming enormous spheres of invisible mass. These dark matter halos are already interacting, their outer edges overlapping. The visible parts of the galaxies may still be millions of light-years apart, but in a sense, the collision has already begun. The mutual attraction has been building for billions of years. When the universe was young, when both galaxies were first forming, they were already gravitationally bound to each other. They've been orbiting around a common center of mass, spiraling slowly inward. Every million years brings them closer. The process is slow beyond human comprehension, but it's been steady and relentless. Nothing can stop it now. There's no force that can counteract the gravity pulling these galaxies together. No mechanism to redirect their paths. The collision is as certain as the rising sun, written into the fundamental laws of physics. It's been written there since the beginning. Now, with both galaxies understood, with their histories and their natures made clear, we can begin to trace what will happen. We can follow the timeline of their approach, step by step, across billions of years. The approach happens slowly. Even at 250,000 miles per hour, crossing 2.5 million light-years takes an enormous amount of time. Andromeda is racing toward us by any human standard, but on cosmic scales, it's barely crawling. The gap closes, but it closes over billions of years. Right now, if you look up at Andromeda, you see it as a small, fuzzy patch. Most people never notice it at all. In 1,000 years, it will look essentially the same. In 10,000 years, still no visible change. Even after 1,000,000 years have passed, the difference will be subtle, detectable only with instruments. The movement is real, but it's glacially slow compared to a human lifetime. Around 3.5 billion years from now, things begin to change noticeably. Andromeda starts to dominate the night sky. What was once a faint smudge becomes a clear structure. You could see the spiral arms, the bright core, the full extent of the galaxy stretching across the darkness. It would be beautiful, enormous, taking up more and more space as the centuries pass. By 4 billion years from now, Andromeda fills a significant portion of the sky. It's no longer just another celestial object. It's a presence, massive and undeniable. The light from billions of its stars bathes Earth in a faint glow. The night sky looks nothing like it does today. Everything has changed. And then comes first contact. The outer edges of the two galaxies begin to overlap. Gas clouds from one galaxy start interacting with gas clouds from the other. Stars from Andromeda's outermost regions pass into the Milky Way's space. Stars from our galaxy drift into Andromeda's domain. The collision has begun. But this isn't like two solid objects smashing together. Galaxies are mostly empty space. The distances between stars are vast, almost incomprehensibly so. Our nearest stellar neighbor sits over 4 light-years away. That's the distance light travels in 4 years, an emptiness so large you could fit millions of solar systems in the gap. When galaxies collide, the stars themselves almost never actually hit each other. Imagine 2 swarms of bees passing through each other. The swarms intermingle, bees from one group flying between bees from the other, but individual bees rarely collide because there's so much space between them. Galactic collisions work similarly. Stars pass by each other, sometimes coming relatively close, but direct impacts are extraordinarily rare. What does happen is gravitational disruption. Every star pulls on every other star. When 2 galaxies merge, suddenly hundreds of billions of new gravitational sources appear. The neat, organized orbits that stars followed for billions of years get disturbed. Stars are pulled in new directions, accelerated or decelerated, their paths bent and twisted by the gravity of passing stellar masses. The spiral arms, those elegant structures that took billions of years to form, begin to distort. Andromeda's gravity pulls on the Milky Way's arms, stretching them, warping them. Our gravity does the same to Andromeda. Both galaxies are being reshaped by tidal forces, the same forces that create ocean tides on Earth, but operating on a galactic scale. The 2 galaxies don't merge immediately. They pass through each other. Andromeda's stars drift through the Milky Way's space, and our stars drift through Andromeda's. But the galaxies themselves continue moving. Their momentum carries them apart again. They separate, pulling away from each other, expanding the distance between their cores. But they're still gravitationally bound. They can't escape. After drifting apart for hundreds of millions of years, they slow, stop, and begin falling back together. The process repeats. A second pass-through, more violent than the first, because both galaxies are now distorted, their structures already disrupted. More stars are flung into new orbits. More tidal forces reshape the remaining structure. This could happen multiple times. Computer simulations show several possible scenarios, but most involve at least 2 or 3 major pass-throughs before the galaxies finally settle. Each pass scrambles the stars more thoroughly. Each interaction transfers energy and momentum, gradually slowing the overall motion, allowing gravity to pull everything together more tightly. Eventually, after perhaps 6 or 7 billion years total, the merger completes. The two galaxies become one. All the stars from both galaxies are now part of a single structure. The spiral arms are gone, destroyed by the repeated gravitational disruptions. What remains is likely an elliptical galaxy, a roughly spherical or oval collection of stars with no clear pattern or organization. Just a vast cloud of suns, orbiting in random directions around a common center. Our sun will likely survive this process physically intact. The chances of actually colliding with another star are minuscule. Space is simply too large, and stars are too small. But the sun's orbit will be drastically changed. We might be flung outward into the outer regions of the new galaxy, far from the center. Or we might end up in the halo, following a long elliptical path that takes us high above and below the galactic plane. The neat circular orbit we follow now will be replaced by something chaotic and unpredictable. The timescales involved are staggering. From first contact to final merger spans longer than Earth has existed. Multiple billions of years, during which the galaxies dance around each other, merging and separating and merging again. Human history occupies barely a flicker at the beginning of this process. But while the stars themselves may survive the collision, the environment around them will be transformed. The structure of space itself changes during a merger, and those changes have profound effects. While stars pass through each other like ghosts, gas clouds do not. Gas is different. When two clouds of gas meet, they collide in the traditional sense. They slam into each other, compress, heat up. The collision creates shock waves that ripple through the material, compressing it further. And when gas compresses enough, stars begin to form. The Milky Way and Andromeda both contain vast reservoirs of gas. Hydrogen primarily, spread throughout the spiral arms and concentrated in dense clouds. This gas has been slowly forming new stars for billions of years, at a steady, manageable rate. But when the galaxies collide, all that gas collides too. Suddenly, instead of a gradual trickle of star formation, there's an explosion of it. New stars ignite throughout the merging galaxies. Thousands of them. Millions. Massive clouds of gas that might have taken hundreds of millions of years to slowly form stars instead collapse rapidly, creating entire clusters in mere millions of years. The rate of star formation increases by orders of magnitude, far beyond anything either galaxy experienced in its normal evolution. These aren't just ordinary stars either. Many of them are massive, hot and bright. The kind of stars that burn through their fuel quickly and end their lives in spectacular supernova explosions. Within a few million years of forming, many of these new stars will die violently, releasing enormous amounts of energy and enriching the surrounding gas with heavy elements. This triggers even more star formation, a cascade effect that lights up the entire merging structure. The night sky during this period would be transformed beyond recognition. New stars appear constantly. Bright blue giants, brilliant and short-lived. Vast nebulae glow with the light of newly forming star clusters. The combined light from all this activity would make the night significantly brighter than anything we experience today. Even planets far from their home stars might receive enough light from the surrounding stellar nurseries to affect their surface conditions. Meanwhile, the spiral structure of both galaxies continues to dissolve. The elegant arms that once traced clear patterns through space are pulled apart by tidal forces. Stars that once followed neat, organized orbits are scattered into chaotic paths. Some are accelerated to high speeds and ejected from the galaxy entirely, flung out into intergalactic space where they'll wander alone for billions of years. Others are pulled inward toward the center, crowding into the increasingly dense core region. Our solar system's fate during this chaos is uncertain in the details, but likely safe in the broad strokes. The Sun probably won't be ejected entirely. Most stars remain gravitationally bound to the merging system, but our orbit will change dramatically. We might be pushed outward into the outer regions of the new galaxy, settling into a slow, wide orbit far from the center. Or we might be pulled into the halo, following an elliptical path that takes us on a long journey above and below the galactic plane. Either way, the neat position we occupy now, embedded in a spiral arm, following a circular orbit at a comfortable distance from the galactic center, will be lost. We'll become part of the disordered elliptical galaxy that forms from the merger, our orbit just one of trillions of randomly oriented paths. At the center of the merging galaxies, something even more dramatic unfolds. Both galaxies contain supermassive black holes at their cores. As the galaxies merge, these black holes spiral toward each other. They're pulled together by gravity, sinking toward the center of mass of the combined system. The process takes millions of years, but eventually, the two black holes meet. When supermassive black holes merge, they release gravitational waves. These are ripples in space-time itself, propagating outward at the speed of light. The waves from a merger of this scale will be detectable across much of the universe. Any civilization with sufficiently sensitive instruments would be able to observe it, seeing the signature of two massive objects spiraling together and becoming one. The merged black hole would be enormous. Combining the mass of the Milky Way's black hole with Andromeda's larger one creates a single object containing the mass of well over 100 million suns. It would sit at the center of the new galaxy, the gravitational anchor around which everything else orbits. The entire merger process is chaotic for billions of years. Stars swing past each other in unpredictable patterns. Gas clouds collide and form new stars. The structure shifts and changes constantly. But gradually, over immense spans of time, things settle. The kinetic energy of all those stellar orbits gets distributed and equalized. The chaotic motions smooth out into a more stable configuration. What emerges is likely an elliptical galaxy. Not definitely, but probably. Most major mergers between spiral galaxies produce elliptical galaxies. The spiral structure is destroyed by the collision, and without that structure, there's no mechanism to maintain it. The stars spread out into a roughly spherical or oval distribution, orbiting in all directions rather than in an organized disk. Astronomers have already given this future galaxy a name, though it won't exist for billions of years. Some call it Milky Way, a blend of both galaxy names. Others prefer Milkdromeda. The name doesn't matter much. What matters is that it will be a fundamentally different kind of galaxy from either of its parents. The transformation from spiral to elliptical marks the end of certain processes. Elliptical galaxies tend to form fewer new stars than spirals. They've used up most of their gas in the merger, and what remains is often too hot or too dispersed to collapse easily. The burst of star formation during the collision might be the last great episode of stellar birth this system experiences. But amid all this cosmic transformation, there's another story unfolding. A smaller, more local story, but one that matters deeply to us. The story of what happens to our own world. Earth won't be here to see the merger complete. Not as a living world, anyway. The galactic collision unfolds over billions of years, but Earth's story ends much sooner. Not because of the collision itself, but because of our sun. Stars age. They change over time. The sun has been burning for about 4.5 billion years, fusing hydrogen into helium at its core, releasing the energy that warms our planet and makes life possible. This process is remarkably stable. It's been running at roughly the same rate for eons, providing a consistent energy output that allowed complex life to develop and thrive. But the sun is slowly getting brighter. Very slowly. The change is subtle on human timescales, imperceptible across centuries or even millennia. But over hundreds of millions of years, the difference becomes significant. And over billions of years, it becomes catastrophic. The brightening happens because of how fusion works. As the sun converts hydrogen to helium, the helium accumulates in the core. Helium is denser than hydrogen, so the core becomes more compressed. This compression makes the core hotter, which makes fusion occur faster, which releases more energy. The sun gradually increases its output, brightening at a rate of roughly 10% every billion years. In about 1 billion years, possibly less, the sun will be bright enough to trigger a runaway greenhouse effect on Earth. The increased heat will evaporate more water from the oceans. Water vapor is a greenhouse gas, so this traps more heat in the atmosphere. That extra heat causes even more evaporation. The cycle feeds on itself, accelerating until the oceans boil away entirely. The atmosphere will be stripped. Water molecules high in the atmosphere will be broken apart by ultraviolet radiation from the sun. The hydrogen escapes into space. The oxygen either escapes as well or combines with rocks on the surface. What's left is a planet more like Venus than the Earth we know. Hot, dry, sterile. Completely uninhabitable. This happens long before Andromeda arrives. Long before the first pass-through of the galaxies. Earth's biosphere ends while the galactic collision is still billions of years in the future. The two events are happening on completely different timescales, driven by completely different processes. The sun continues evolving. Around 5 billion years from now, roughly the same time the galactic merger reaches its final stages, the sun will exhaust the hydrogen in its core. When that happens, fusion stops temporarily. The core contracts under its own gravity, heating up until it becomes hot enough to fuse helium. Meanwhile, hydrogen fusion begins in a shell around the core. This changes everything. The sun expands enormously. It swells into a red giant, growing to hundreds of times its current diameter. The outer layers cool as they expand, giving the sun a reddish color, but the total energy output increases dramatically. the sun becomes thousands of times brighter than it is today. Mercury will be consumed entirely, engulfed by the expanding solar atmosphere. Venus likely meets the same fate. Earth's future is less certain. We might survive, orbiting just outside the sun's swollen edge. Or we might be swallowed too. It depends on exactly how large the sun becomes, and that's difficult to predict with precision. Even if Earth physically survives, it will be scorched beyond recognition. Any remaining atmosphere will be stripped away. The surface will be heated to temperatures that melt rock. Nothing we would recognize as Earth will remain. Just a dead, possibly molten sphere orbiting inside or just outside a dying star's outer envelope. So the galactic collision and the death of our sun happens simultaneously, both reaching their climaxes around 5 to 7 billion years from now. But they're independent events. The collision doesn't kill Earth. The sun does. Even if the galaxies never merged, Earth would still face the same fate. The solar system itself will likely survive the galactic merger in some form. The sun probably won't collide with another star. The outer planets, Jupiter and Saturn, and the ice giants will probably remain in orbit, though their paths may be altered by gravitational encounters with passing stars. The sun will continue its evolution regardless of the galactic environment around it. Eventually, the sun will shed its outer layers entirely, creating a planetary nebula. What remains is a white dwarf, a dense stellar remnant about the size of Earth, but containing most of the sun's original mass. This white dwarf will cool slowly over trillions of years, radiating away its remaining heat into the darkness. Any planets that survive the red giant phase might continue orbiting this white dwarf. There are such systems known in our galaxy already. Dead stars with dead planets locked in eternal orbits, cold and dark and utterly lifeless. But the merger creates trillions of new stars. Many of those stars will have planets. Some of those planets might be in the habitable zones of their stars, the regions where liquid water could exist. Life might arise on those worlds. Civilizations might develop, looking up at their sky and wondering about the universe they inhabit. They would see a very different galaxy than we do. No spiral arms, no clear structure, just an elliptical distribution of stars, most of them old, the galaxy's violent youth long past. They might study their galaxy's history, finding evidence of the ancient collision that formed it. They might even discover that two separate galaxies once existed, where now there is only one. They would be living in the remnant of our galaxy's death and rebirth. Witnesses to a transformed cosmos, inhabitants of a world that couldn't have existed without the collision we're discussing. The end of one era, but potentially the beginning of another. Galactic collisions are not rare. They're not catastrophic anomalies or cosmic disasters. They're a normal part of how the universe works. Most large galaxies we see today are the products of mergers. They grew by consuming smaller galaxies or by colliding with galaxies of similar size. The Milky Way and Andromeda are simply continuing a process that's been happening since the first galaxies formed. Look at the Hubble Deep Field images, photographs of tiny patches of sky that contain thousands of distant galaxies. Many of those galaxies show signs of interaction, distorted shapes, long tails of stars, bridges of material connecting one galaxy to another. We're seeing collisions in progress, frozen at various stages. Some are just beginning, galaxies approaching each other across the void. Others are in the midst of merger, their structures already heavily disrupted. Still others are settling into their final forms, elliptical galaxies born from violent collisions. The antennae galaxies are a famous example. Two spiral galaxies in the midst of merging, their interaction creating long streamers of stars that extend far into space like insect antennae. The collision triggered intense star formation, visible as bright blue regions where massive young stars have ignited. In a few billion years, those two galaxies will be one. The process is identical to what will happen here, just happening to someone else, somewhere else. Computer simulations of galaxy mergers are remarkably beautiful. Scientists can input the properties of two galaxies, their masses and sizes and velocities, then let physics calculate what happens. The simulations show swirling patterns of stars, spiral arms stretched and torn, tidal tails flung out into space. They show multiple pass-throughs, the galaxies orbiting each other in an intricate dance before finally settling. The patterns are chaotic but not random. They follow clear physical laws. These simulations reveal that mergers are creative processes, not destructive ones. Yes, the original structures are disrupted. The spiral arms dissolve. Individual stellar orbits are scrambled, but new structures emerge. New stars form in unprecedented numbers. The merged galaxy contains everything the originals had, just rearranged, reconfigured into a different form. This is how galaxies grow. Small galaxies merge to form medium ones. Medium galaxies merge to form large ones. The process has been ongoing for over 13 billion years, since shortly after the Big Bang, and it will continue into the far future. The Milky Way and Andromeda won't be the end of it. The local group contains more than 50 galaxies, and eventually they'll all merge together. The smaller ones will be absorbed first, over the next few billion years. Then, after the Milky Way and Andromeda have become one, that combined galaxy will begin accreting the remaining members of the group. The Triangulum galaxy, the third largest in the local group, will likely merge with the Milky system at some point. More mass, more stars, more growth. In the far future, tens of billions of years from now, the local group will be a single, giant elliptical galaxy containing all the stars from all its current members. By then, most of those stars will be old, red, and dim. The bright blue stars will have died long ago. New star formation will have mostly ceased. The galaxy will be a vast collection of aging suns, slowly fading as they exhaust their fuel. Beyond the local group, other galaxy groups and clusters are undergoing similar processes. They're merging internally, forming larger and larger structures. But those structures are moving apart from each other. The expansion of the universe carries distant galaxy clusters away from us faster than gravity can pull them together. Eventually, every galaxy cluster will be isolated, separated from the others by expanding voids of empty space. In the extremely distant future, hundreds of billions of years from now, any observers in our galaxy cluster will look out and see nothing. The other galaxy clusters will have receded beyond the cosmic horizon. Their light will be stretched to infinite wavelength by the expansion of space. They'll simply disappear, leaving our merged galaxy alone in an increasingly empty universe. But that's far beyond the timescales we've been discussing. The collision with Andromeda happens in the relatively near future, cosmically speaking. 4 billion years is a long time by human measures. but it's less than a third of the universe's current age. It's the near-term future of our galaxy. We won't be here to see it. Humanity almost certainly won't exist 4 billion years from now. Earth's biosphere will end long before then. The sun will evolve and change and eventually die. Everything familiar will be gone. But the process will unfold whether we're here or not. The galaxies will merge according to the laws of gravity and motion, following paths determined billions of years ago. There's something both humbling and comforting about that. The universe operates on scales so vast that our entire existence is barely a moment. Yet we can understand it. We can calculate the orbits of galaxies billions of years into the future. We can simulate collisions we'll never witness. We can look at distant mergers and recognize what's coming here. On a clear night, you can see Andromeda with a naked eye if you know where to look. That faint smudge in the constellation. It's easy to miss among the brighter stars. But it's there and it's approaching. It's been approaching since long before we existed. And it will continue approaching long after we're gone. The collision is written into the structure of space itself. Andromeda and the Milky Way are bound together, falling toward their inevitable merger. It's been happening all along. We just happen to be here briefly to notice it.